All right, so I wanted to give a little update because I found out, of course, I made a whole bunch of mistakes in my previous videos. Basically, I just said a whole bunch of things that were not necessarily 100% accurate. I mixed up Riemann spheres with block spheres. Time cannot be randomized because it has no operator. So these two main things have kind of affected our theory of quantum gravity a little bit, but actually for the better, because like obviously when things are correct they lead to answers, and so we have to get things correct, and when we get things correct we get better answers. All right, the answers improve. So um, let's deal with the Riemann sphere and the block sphere differences, and that might be better to look at the standard model for that. So the Riemann sphere is something that has to do with complex um, uh, analysis. But what we're really doing in quantum mechanics is using block spheres, not Riemann spheres. Block spheres are unit spheres, okay? So they just have a unit one here. The rotations around the sphere, around the six basis states. You can flip between these six basis states. Imagine like a dice, a six-sided die. So you can end up with one face. Um, and we can we can roll the dice based off of these three different matrices. It's the SU2 group. Um, discussed this sort of in another video. Uh, here's a wave function, and here's how we can basically superimpose zeros and ones, which is essentially going to be, uh, in this particular case, we're just using a regular old block sphere. We're in the SU2 group. We're talking about spin up and spin down. When you start to talk about the U1 group or the SU3 or higher groups, then these would represent different states. But in this particular case, it's just ups and downs in terms of spin. And then we can superposition the two different ones, just like this. You call it a plus and a minus. Or we can also go to the imaginary version, which is going to be, uh, well, you know how it is. Quantum mechanics, we have to use the imaginary plane. So we have these three different ways that we can do this, and get the plus and the minus. This is the plus imaginary, plus minus imaginary, and these are the six different states. So we get six states from three generators. Okay, this is, you can see there's one loop here, and then there's another loop here, and there's another loop that would be going right here, which I should draw. I don't really want to draw it because, it's kind of, yeah, I'm not going to draw it. There's another one right here. You can see it go right here. That will be the third generator right here. I'm not drawing it just because yeah, I was going to mess up the whole thing. So, yeah. But we have three generators, which gives us six basis states. That makes sense. These basis states are very polar opposite states. So you're trying to maximize the distance between these two states. And this very interesting. What I'm actually watching right now is a video from um, Veritasium, and he his video is actually giving some light and some progress towards the theory that we're looking at, but we will ignore that for the time being. So it's kind of interesting, but whatever. So these spheres, again, they're kind of just like coins that you're flipping or dice that you're rolling, but they're really polarizing because you can't see anything else except for the one face, and the states shift instantaneously. Okay, uh, so usually when you have to shake an 8 ball, it takes you a while to like go through, or when you're flipping coins, it takes a while. But these states are basically being pressed against this tinted window so you can see just that face, and they're flipping back and forth instantly. So it's pretty pretty interesting how that works. But we'll discover what this really implies later. And remember, all these states, basically, first you have to roll the die, you get infinite probabilities, and then one single state is the collapse of the wave function, essentially. So one of these things pops up, and then you realize, oh, you've measured it up, you've measured it down. And so you can think of like the universe in terms of time here, space-time, like this thing that's just shifting through. It's like this fields that are sort of very polarizing, and they're following time in one way path. Of course, they're really going in all directions, but they're basically time is a one directional path. You can't go backwards in time, so that's why we have to deal with that. So you're essentially getting a net quantum moment in whatever direction of time you want to point in. I'm getting a net quantum moment, and we're going to discuss how time seems to have a magnetic component to it. So let's that was just a review of the block spheres, just to kind of realize that this is how we can flip between quantum states, is we require this little block sphere, unit sphere. It's like we're rolling these dice or flipping coins or a magic 8 ball. Now, the magic 8 ball, let's go back to here. Oh, I think I've already opened it right here, right? It's the indication there. Okay, so here's the magic 8 ball right here. And, well, I did click on this because you were probably looking for the magnetic model. And I believe we have found it. Okay, and this is why. All right. So let's recall that our U1 group requires a loop. Uh, and we sort of discussed this like way over here, I believe. Well, we're really looking at these wave functions that represent these particles in boxes, L's. We are essentially turning the L into a one-dimensional loop. All right. And I don't know if we can see that one-dimensional loop anywhere over here, but I like to draw these things, so I can draw it again if necessary. Sure. So basically, once we go through the 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 wave function for the particle in the box here, you can see this is the form. This is general standard form here. We're going to sum up from 1 to infinity. You can imagine this as Planck lengths. Okay, so you actually have the Planck length is going to be L. And this is an integer amount of Planck length, so we're just connecting a whole bunch of different Planck lengths, and we're just making essentially a continuous Planck length, multiple Planck lengths here, all the way to infinity. We've already sort of discussed all this in a different video, but the idea is that we get this zeta 1/2 if we do that, which is fine. And we get all this other stuff. This tells you about the sine stuff, and then we have to normalize it, so we get some. We have to decay uh, these things in order to do this. Okay, and then over here we need to consider the energy, and that requires the time. So we're taking the derivative of time, and when we do that, we can now consider the time value here for the zeta function. Because if we're considering the time value here for the energy, we can also consider the time value for the wave function. There's nothing too crazy here because this one requires IT, and so we're just doing another IT here. This is absolutely fine. The wave function is going to evolve, or sorry, the zeta function is going to evolve with time, just as the wave function itself is going to evolve with time. So all this pops out of just a single old, regular old particle in a box length L. Nothing crazy. We're just, yeah, we had to sum 1 to infinity, which is usually not really done, but we're doing it and we're assuming that these lengths are Planck lengths, integer quantities of the Planck length. And we are decaying it by this factor here to make sure that as we go to infinity, the infinity doesn't blow up and diverge and stuff. Okay, so we're decaying this. And so now we have randomized the position over the length L. We're randomizing these L's, so we're going to appear in some random size box, random loop size, I suppose. And that's fine. And we need to get smaller boxes to be more likely. Okay, that's what the decaying factor is. This is the decaying. And we're looking at energy from time. Okay, so we need the timeline. So what happens is we're just looking at a single one of these little things. Now, these aren't circles yet, although they should be circles. We need to turn them into circles in a moment. Um, I believe this is how it turns into the circle here. But yeah, um, so here are the wave functions sort of evolving over time. We're going to assume that nothing really changes from here to there, okay? But yeah, so nothing's really changing too much from here to there. And then we have an area. This, I'm sure we know about the progression of the distances of the uh, Riemann hypothesis, the zeta zeros. This is essentially giving us, here is our loop. I can draw this finally. See if I can draw a nice circle here. Now I know I said length L, but that's because what we're really doing here is we're getting a wave function. And this wave function here is going to be pointing in some direction. This is how these groups essentially work. And you could spin around this circle, and then you could either be a 1, or you could be a 0, or you could be a I, or no, sorry, you could be a 1, or you could be a negative 1, or an I, or a negative I. And this is just the U1 group, okay? U1 symmetry. Basically, this is the graphic version of what's happening, and this is the matrix. There's like a, well, it's not a matrix, this is more like scalars. So, but yeah, there's all these different scalars. We call it e to the I theta. Right? E to the I theta. Or no, e to the theta time or something. I'm pretty sure it's just e to the I theta. Yeah, yeah, yeah. Okay, so it's e to the I theta. Okay, so now this is essentially the representation. This is the equation. This equals 1. Sense. So U1 group gives us this, which gives us essentially this situation here. I'm calling it either its wave function. And this no longer looks like an L, but that's fine because these L's, they're actually essentially integer quantities of this wave function here. So the radius is L, and we're sort of spinning it around here. So at every point, it's always still L. There's no change here. It's just that um, we've now decided to get a certain amount of wave functions, sub wave functions. This is the grand wave. You could split up wave functions to smaller wave functions. But, no, I believe this is the length of the wave function. Remember that uh, this is where Snell's law came into play. Well, we have to normalize these wave functions, and all wave functions squared equal 1, which is exactly the same type of thing that you get when you have the Snell's law situation, um, where sine of an angle divided by the square root of a length is equal to a constant, which is equal to 1. If you do this particular operation, you could square it, normalize it, and all wave functions are equal to 1. So essentially, this is Snell's law right here. And that is what was kind of blowing my mind because the video from Veritasium, thank you very much, sir, is the single rule underpins all of physics it popped up right here, and I was just like, what? That's true. Yeah, there's a sine of an angle here. It's divided by the square root of a length, and all of these wave functions are equal to 1. And that's Snell's law. Okay, but let's go ahead and I'll figure out what the implications of that means later. But essentially what it's trying to do is I think what it's doing is it's minimizing the time between um wave functions or something. So that's kind of cool. But yes, now we've designated these L's to be integer lengths of wave functions, which are just integer lengths of 1, which is fine. Now we've got this wave function here. Uh, and yeah, so so essentially these things are H bar. I forgot. These things I believe they're H bar. No, not H bar, but if we were to convert this into like an area or something, uh, we get we get an H bar command of this, I believe, and it could require a 2 pi in front of it, but we're essentially going to realize that there's H bar. What does this mean? It means that essentially this is the Planck length H divided by 2 pi. So you can see how you might be getting sort of a circumference out of this, or a type of area, or some factor that's not necessarily just length. Although this is a one-dimensional area, so it's like, what? How are you getting a one-dimensional area H bar? Believe me, H bar. Um, it always works. I know it seems weird, but this is essentially this is actually correct for whatever reason. But yeah, so we're going to go with that and assume kind of these things. Um, the area around this loop gives us h r over 2 pi, um, and uh, and the length is this, and the U1 group, and all that good stuff. So this is cool. Now we just needed a timeline, and you can see how the loop would essentially be here, and you get a little timeline popping out, popping out the loop right here. Move this I or something about that. So you get the time. I'll try to hurry this up because I know we're getting a little bit more out there. But here's the timeline, and this is the imaginary timeline, which is not continuous, so it's a little bit rough. So we had to parameterize that in order to take derivatives. I mean, that's fine. Um, and then this is very interesting, this little shape right here, because this is our little thing, and it's progressing through time, which is what we need. This is what this equation describes, as long as we assume these terms. We randomize the L's now. We're randomizing energy levels, which is fine. Um, and it's okay to get some things wrong, but you can see how we get a lot of things right, and it leads us towards closer things. So anyway, where are we? We'll forget about the dark energy because we talked about that in a different video. But let's come back to the fact that we're not randomizing time. In fact, if we want to go through the time line, uh, usually like you have to follow, like if you move through space, you're moving through time, yeah. But even if you're not moving through space, you're still moving through time. So that's why just time is essentially a forced progression, and that's why we have to use IT, especially if we're doing this quantum stuff. So you could take a derivative of regular time or IT. I mean, it's the imaginary time line, so you have to take time derivative and then multiply by I to get a meaningful answer. That's kind of what this is going for. Okay, I don't know if you've seen the Schrodinger equation, but it's a pretty basic one. We have to take the time derivative of the wave function, and then we multiply it by I. and h bar. But it's interesting because let's go back to these loops. If we know about magnetic moments, magnetic moments are interesting too because apparently we have a magnetic moment here. Uh, it could be an electron going through here. It's fine, but it's really not. It's a wave function, actually. It's a wave function going around here. So let's just consider that. But so usually for the magnetic moment, you calculate it by doing n, and then you have some current, and then which I'll just call it. It's a capital I in this case because it's a I is an imaginary thing, but this is current, which we'll just call it dq over dt in this case. Actually, might be better. And then we're gonna multiply this by an area. Okay, so this is just a regular old magnetic moment. Has nothing to do with any of the stuff we're quite honest right now. But yeah, so let's build up to it. So this is regular magnetic moment. But what we can do is we can actually figure out a temporal moment. Temporal moment. And the temporal moment, we already did it here. The time flux. This is the time flux. I'm just replacing the q for a wave function because that's what's going through here. And we are replacing a with h bar. Okay, so if we do that, what happens is we get this. That's what happens if we replace the area here, we understand that we're just taking an h bar length here, a little Planck length, and spinning around 2 pi, and we get a little area from that, and we're putting that right there in our equation. Here we're taking the derivative of the psi here, the length, the psi, whatever you want to call that thing, wavelength, and it's in imaginary time, so clearly we have to multiply this thing. So taking a time derivative here multiplied by I, however you want to think about that. And the n, this gives us the n energy level. Remember that if we take um, this is supposed to be equal to energy. In fact, it's equal to the energy right here. So that is quite fascinating. It's quite fascinating that the Schrodinger equation is actually just a temporal moment, a magnetic moment converted to a temporal wave function moment. Uh, we just gotta let that sink in for a little bit because this kind of uh, I kind of saw this. I kind of figured, just kind of noticed this earlier. I was just like, if you just make a little bit of adjustments here, you're gonna get certain energies, quantized energy levels in a box, and I do believe that these energy levels are supposed to be the same sort of distance apart, as far as I can recall. I mean, I know that there are some versions where this does not happen, but this is kind of more like a very basic version of what we're looking at. And so therefore, uh, the sort of most ideal energy levels are equally spaced. Let's just double check that based off of some of the notes we've taken earlier. Um, so energy levels in a box. I'll have to do a little bit of double checking on all that stuff. Could be that the energies decrease a little bit, which is fine. But, regardless of the matter, we're getting this issue that we have a sort of a scaled version put an n. I don't know whether we need to put uh, how much more we have to change this. There's an n sort of implied here in that yeah, it's not gonna happen at just one level. You can get to the next energy level and the next energy level and sort of scale this up and get higher energies. And all we had to do was to take the derivative, the time derivative of the wave function, and then well, it's an imaginary derivative, so let's multiply this by I. It's just one, and then we have h bar, which is the area, and then we have basically the n situation. So huh, we have we have we have derived, in fact, the Schrodinger equation from this little thing sort of backwards. It's weird, but I mean, the equation pops out of the math that we sort of is. It's kind of obvious that it would be there at some point. You end up finding it somewhere. There it is. So now, now what that means, uh, yeah, this is kind of the reasoning of why you would want to consider. It's like pi, why you might want to consider this area of a one-dimensional loop pi wave function squared. I mean h bar, right? Uh, I believe this is the general sort of way that we represent the area of a one-dimensional loop in the U1, as far as I know. Anyway, so yeah, so now if we look at the issue that we had before about time not being random, well, that's fine because if you just follow, if you don't randomize this progression and you just continue to move forward, what happens is these these energy levels or these time snippets, time bits shrink and they become really, really, really small, wafer thin. And so any type of little perturbation, left or right or up or down, whatever direction you want, is going to cause a tiny perturbation. And the perturbation is going to affect all of the fields around it because all this stuff is done in such a wafer thin, like literally such a small snippet of time. What we're doing is we are moving through the zeta zeros, and this the snippets are getting snip smaller and smaller and smaller, and that's why, in fact, the dark energy is present because we are causing a space expansion. We need this derivative, sorry, the differential area here to remain fixed. And so, if we're shrinking one um sort of at the speed of light, we have to expand the other at the speed of light as well. Um, and so basically that's how you get the dark energy out of that. It's quite interesting. But yeah, any type of little perturbation is going to cause things to happen in the field. The real zeros are going to be smushed right against each other. So all the real zeros are smushed against each other. Uh, all of the um, sort of partially real and partially imaginary zeros are going to be all smushed together. The zeros and the imaginary zeros, these things are going to be smushed together, and they're going to be because this thing is wafer thin, and so you can see how like this zero here, this is just a regular real zero here, and this is a real zero here, but in between, you've got the time bits and stuff. So all these things are sort of like getting really, really close together. So they're of course going to all interact together, and of course the zero imaginary, double zero imaginaries, those are all just dark matter fields and stuff. Should probably because they're more contained in the electromagnetic field. Yeah, yeah, yeah. So, so basically, the cool thing is um, that all of the particles kind of pop out of these little perturbations in the Higgs field, which is which is cool. So it really doesn't matter which particle really considering in this box here. But what we're actually putting in the box is wave functions. So uh, any wave function, this could be for any particle, and we're just kind of tossing it in there. Um, so that's what's really cool about what, what's that? And yeah, but that's definitely correct. Now, yeah, awesome. So, what we were thinking about here was like, yeah, there's no random um time sort of appearing, which is fine. Time is forced in one direction, but that's excellent. In fact, that polarizes these loops because as soon as you start to like move in one direction, that's fine. But if you want to flip around to the other side, you're gonna instantly flip around. Okay, it's gonna be just it's a thing where like this whole thing just flips to the other side. And that just means that we have to think about two moments, one that's going up and then the one that's going down. And this gives the photon, the U1 group just describes the photon. So this is the EM group right here, the electromagnetic uh, group right here. But this is just the photon polarization. So you get two moments from this U1 group. You can see that there's one this way, and then you can flip it around and go the other way. So you get two sides. That's what the photon polarization phenomenon is represented. So that's quite interesting. This also happens when you go to the SU2 group, although this is going to be, I believe, spin directions. So you get six different moments, six different sort of quantum states there, uh, even though you only have two directions, which is kind of crazy. But it's kind of cool how you can see if we start with you could start with just a few things and then all of a sudden it just multiplies into a whole bunch of things. Because if you go into SU3, all of a sudden you get 16 moments. So it's kind of crazy. But what these things are doing is they're essentially flipping states. And those are the magic A balls that we were talking about from the beginning of the video. And this is sort of all just pushing through time. I had drawn that. You can think of just a zillion magic 8 balls, right? And they're all sort of pushing through. Let me open the correct one. Pushing through this little thing right here. So these are just the polarizing fields just kind of going in DT direction and sort of forcing all these magnetic moments to sort of basically just polarize and become certain states. And that's forcing things into certain states, is these little essentially magnetic monopoles. And why do I call them magnetic monopoles? Is because we had the magnetic moment there. We derived this from a magnetic moment. And if you you can't just put a Gaussian sphere around the whole thing because if you do that, the bottom side doesn't have anything really going on for it. So you really can only do a semicircle here. So that's your Gaussian surface. So as soon as you flip this around and polarize it and go to the other side, you now get the other half of the sphere. So now you get this sort of double-sided magnetic moment, uh, where well, you basically get a magnetic monopole out of this. And the magnetic monopole is, in fact, the quantum state materializing, as in these tiny, tiny little things. These tiny little quantum states, these tiny little wave functions that are just materializing, those apparently the time flux right here. It's literally this. Those are the magnetic moments. It's right here, and you can see it. and these are the magnetic monopoles. You can see the Gaussian sphere would go around this. You gotta have two hemispheres, two semicircles here. You can flip it around, and you get basically that the there's a magnetic component that pops out of this thing. Essentially, it's not necessarily exactly the B field per se, but it it's derived from the same expression of the magnetic moment, and it's very strange indeed. It gives us the Schrodinger equation, and it sort of completes what we needed. We needed all of this. This all makes so much sense. These polarizing states, and any little perturbation in these fields are going to cause vacuum expectancy values because there's changes in energy. So, you know, whether it's randomized or whether it's just a little perturbation for whatever reason, you know, just literally the spinning around of these quantum states is going to cause perturbations. So, you know, um, belief essentially covers what I wanted to discuss today. Trying to figure out what's going on here. So, yeah, it was definitely a revelation when I sort of noticed this Schrodinger equation popping out at me, and I was like, oh, okay, I guess it's right there. If any more insights come from the Snell's law situation, we'll have to see. But for now, here is the magnetic monopole. It's actually just the Schrodinger equation. It's the left side of it. It's the one where um, you know, why are we taking the time derivative of a wave function and multiplying it by I and h bar? It's because it's a magnetic moment. It's because it's a magnetic monopole. That's why. An electron turned. I know, right? Yeah, the currents are super slow, right? It oscillates with the charges. Yeah, yeah. My teacher was describing that the other day, I believe. Um, so neutrinos are a big mystery. Yeah, I know, right? I don't or were they do I have a few ideas of we got to go back to the standard model here. I feel a few ideas of why these particles are popping out. Um, I'm pairing together zeros in specific ways that yield the standard model here. Although I know that there's more particles than just the standard model, so that's why I'm a little skeptical of this. It worked perfectly. Obviously, everything worked perfectly. Everything, lined up. You get zero mass from these things here that are BIs. You get mass from the A's, alphas. You get charges from either positive or negative BI. Uh, mass from the A by itself. All these things work perfectly, a little too perfectly. We get the perfect amount of spin, states, everything works absolutely friggin' perfectly, which is a little bit skeptical. Why is everything working so perfectly just from pairing random zeros together? Like, what? I mean, I'm pairing zeros together in various ways. That's all I'm doing here. I'm just real zeros, the imaginary zeros, and I'm thinking about the Riemann hypothesis and the axes that come from that. You're just gonna get the trivial zeros, which are the real zeros, and then you're gonna get the imaginary zeros, which are uh, the imaginary zeros. And you see how they're just basically getting really close to each other uh, when we have to go through time after a long time, right? Over here, you see how the wafer thin this happens. Like these things just start to squeeze together, and the zeros start to become closer and closer and closer, kind of together. Even though, you know, it's all unique. They're all unique zeros. At least the imaginary ones are. But the real zeros are not. That's why gravity is one-sided, is because the real zeros are trivial. They have the same spacing. Um, the imaginary zeros, they don't have the same spacing, so they cause these dark matter halos to just kind of spiral around everywhere in these weird shapes. And the zero paired with a real zero, the imaginary zero paired with the real zero gives us just like regular old like gauge fields, uh, electric fields, magnetic fields, all those types of fields that require the real and imaginary part going back and forth. So I'm getting like basically as more math comes out of this, more accuracies and more like, huh. I'm starting to believe in the unique zeros. I'm starting to believe in the zeros, the magical zeros. I'm starting to believe in them. I'm starting to get more and more confident in these zeros. But I think the nail in the coffin is going to have to be the the particles that we look at right here. Uh, so just come into I remember things. Ooh, interesting. Yeah, I'm sure that there has to be something with the primes. Oh shit. Wait, really? You're saying that shapes can't contain a prime number of points? Or, well, we'll have to see, because if that is the case, all these zeros are sort of trying to reveal locations of the primes. And so if there's a prime there, but you're saying that you can't have prime numbers of points, then it would make sense that there would be zeros at the prime points. That's that's super interesting. We're gonna have to do some research on that and try to map the like the mapping points um, that cannot be, and see if we can to for certain shapes. Yeah, maybe a circle, and maybe see if we can match that to the zeros on the strip. You know, I've tried many different ways to try to map to the zeros, uh, and none of them have worked, except for linear transformations. Linear transformations uh, lead to if you do a linear transformation forward and then a linear transformation backward, you return back to the original states. I mean, obviously, but that's kind of the interesting thing. So, I mean, yeah, but we'll have to go ahead and check to see if we could take like maybe a circle or some various shapes, and sort of map them to the Riemann zeros if those points are not possible. That would be quite interesting. We'll have to see. We'll have to see. And then we'll also have to see if we can derive more particles using the same idea here. Maybe there's just all variations on these particles. If that's the case, if all the other particles are just variations of these particles, then I do believe that these pairings are correct. But we'll have to do some research. I'm not really too familiar with all that stuff. But I think this is where we're gonna have to call it a day here, because I have essentially finished all of the crazy stuff I'm talking. Oh yeah, no, there's one last thing, huh? I have to discuss the anti-de Sitter space. Because, well, remember as we start to stack these loops, last time I did mention that we come to a real volume here, But we did have some very strange things happening in this real volume. Notice this saddle shape. -1, -1, 1, 1, 1. So it's a saddle shaped volume here. That's anti-de Sitter space for you. Um, I didn't realize that I was just deriving anti-de Sitter space just by like stacking a bunch of zeros together. But do I have to pull up a picture? I mean, the, I mean, what the heck? So this is anti-de Sitter space, and it actually leads to the conformal field theory that is on the boundaries, and we'll have to do some more research on that, all that nonsense. And then here's the magnetic moment. Anyways, guys, y'all have an awesome night. I'm just gonna be basically what we're gonna have to uh, finish with. Peace, guys. Thanks.